There are more numbers between 0 and 1 than there are whole numbers, even though both lists go on forever. Watch the yellow whole numbers try to claim one blue decimal each. 1 gets 0.2, 2 gets 0.71, 3 gets 0.03, and the matching continues down the screen forever. It looks fair. Every decimal should eventually get a partner, except I can use the finished list to manufacture a decimal that it missed. Every time. Rearrange the list. Use a clever formula. Run it for 1,000,000,000 years. I don't care. The missing number can be built directly from whatever list you give me. So these two infinities cannot be the same size. That sentence is deeply rude to common sense. Infinity was already the word we used when counting stopped working, and now apparently counting comes back wearing a fake mustache and starts comparing infinities. The trick is hidden in this grid of digits. Keep your eye on the pink diagonal. In a minute, we're going to change those digits and make a number that dodges every row. But first, we need to agree on what same size could possibly mean when neither collection ever ends. I got stuck there the first time too. You can't count to the end because infinity has been inconsiderate enough not to provide one. The way around that missing endpoint is to stop asking when counting finishes. Instead, ask whether every object can get exactly one partner. If 5 chairs hold 5 people, the sets have the same size. We don't need to count either group. We can just watch everyone sit down. The same idea survives infinity. Pair whole number 0 with even number 0, 1 with 2, 2 with 4, 3 with 6. The rule is simple. Send n to 2n. Every whole number gets an even partner, and every even number comes from exactly one whole number. So there are exactly as many even whole numbers as whole numbers. Yes, even though the evens are sitting inside the wholes and seem to leave half of them behind. Finite sets don't get away with that. Infinite sets do. This is the first weirdness tax. If a perfect pairing exists, the infinities have the same size. Mathematicians call the pairing a bijection, which is a lot of syllables for nobody being left without a dance partner. We'll call an infinity countable when its members can be paired with 0, 1, 2, 3, and so on. The obvious examples qualify. The less obvious ones start causing trouble, because even collections that look much denser can sometimes be threaded onto one endless list. So before blaming decimals, we should test a nastier candidate, all the fractions. Fractions look like they should overwhelm a single list. Between 0 and 1 alone, there are infinitely many of them. Then there are infinitely many between 1 and 2, and between every neighboring pair after that. Still, the fractions can be listed. Put every positive fraction p over q in a grid. Numerators run across, denominators run down. Now walk through the grid diagonally. 1 over 1, 2 over 1, 1 over 2, 1 over 3, 2 over 2, 3 over 1, and keep zigzagging. Every possible pair of positive integers lies on some diagonal, so every positive fraction eventually gets visited. We skip repeats like 2 over 2 because 1 over 1 already claimed that value. Then weave in 0 and the negative fractions. Done. Every rational number has a seat on the whole number bus. This felt illegal when I first saw it. A fraction is hiding between any two different numbers you point at, so the number line is packed with them. Density and size turn out to be different ideas. A crowd can be everywhere and still be countable. That matters because decimals also look packed. Maybe we can perform another clever zigzag and list those too. People tried variations of exactly that thought. The problem is that a decimal carries an endless sequence of choices, and those choices let the decimals fight back. To see the difference, we need to stop looking at where the numbers sit on a line and look inside their digits. A decimal between 0 and 1 is an instruction that never quite stops. Choose a first digit, then a second, then a third, forever. Even if most digits are boring, the full infinite sequence determines the number. 0.5 is really 0.5000 forever. 1/3 is 0.333 forever. And a number such as 0.1, 01, 101 carries its own endless pattern, whether that pattern has a nice description or behaves like spilled rice. For a fraction, the digits eventually repeat. That's a useful fact, though we won't lean on it yet. The full set of real numbers also contains decimals, with no repeating tail at all. Here is the temptation. Make a list anyway. Row 1 gets the first decimal. Row 2 gets the second. Perhaps sort them by some clever rule we haven't discovered. If every real number appears somewhere, then the whole number infinity wins again. And notice how generous we're being. We won't demand that the list be computable, tidy, or remotely sane. Somebody can hand us a magical completed list containing one infinite decimal on every row. Cantor's move begins after that list already exists. He doesn't complain about its ordering. He reads one carefully selected digit from each row. That diagonal gives him enough material to build a saboteur. Here comes the part worth stealing. Suppose row 1 begins 0.1384, row 2 begins 0.4917, row 3 begins 0.7752. The actual digits don't matter. Take the first digit from row 1, the second digit from row 2, the third from row 3, continuing down the diagonal. Now build a new decimal by changing every selected digit. We'll use an easy rule. If the diagonal digit is 1, write 2. Otherwise, write 1. This gives a new mint number. Why can't it be row 1? Its first digit was deliberately changed from row 1's first digit. Why can't it be row 2? Its second digit differs from row 2's second digit. Row 7 gets caught at digit 7. Row 10 million gets caught at digit 10 million. Every row has one specific place where the new number disagrees with it, so the number isn't anywhere on the supposedly complete list. And yet it is a perfectly valid decimal between 0 and 1. That's the contradiction. The list claimed to contain all of them, and its own digits gave us instructions for making one it excluded. Watch the mint row slide across the entire grid. It bumps away from row after row, always at the highlighted diagonal position. This one frame is the whole engine. An infinite list has only one row per whole number. The diagonal number uses its nth digit to escape the nth row. There is nowhere else for the list to hide it. That escape is the answer. With one annoying decimal trapdoor we should close before somebody falls through it. Some numbers have two decimal spellings. 0.5 followed by endless zeros equals 0.4999 forever. If our new number accidentally used a tail of nines, it might differ as a written string while secretly naming a number already on the list. This is why the changing rule used only ones and twos. The constructed decimal can never end in repeating nines, so it has one unambiguous value for our purpose. Tiny repair, proof survives. Honestly, decimal notation is being a little dramatic here. The important fact remains. Any proposed list of real numbers between 0 and 1 misses at least one. We didn't inspect every row in sequence and eventually find a gap. There is no eventually. We defined all the mismatches at once with one rule. That distinction is doing serious work. A very long finite list can be searched. An infinite list has to be defeated structurally. The diagonal construction is a machine that accepts any infinite list and outputs evidence of failure. Shuffle the rows, duplicate entries, use binary, hire a faster computer. The machine keeps working. So the real numbers are uncountable. Their infinity is strictly larger than the infinity of whole numbers. But larger deserves a careful meaning here, because we have proved that one pairing is impossible. We still need to see why the whole numbers fit inside the reals in the other direction. The easy direction is that every whole number can be placed among the reals. 0 maps to 0, 1 maps to 1, 2 maps to 2. Nothing mysterious there. So the reals contain a copy of the whole numbers. If a perfect pairing also existed, their sizes would match. The diagonal argument kills every possible pairing, because any pairing would create a list, and every list misses a real. That is what strictly larger means for infinite sets. The smaller set can inject into the larger one, while no bijection can match them completely. We usually name the size of the whole numbers Aleph null. The real number size is often called the continuum. The symbols make this look tidier than it feels. Aleph null is already endless. Add one item and its size doesn't change. Double it, still no change. Multiply it by itself, as our fraction grid effectively did, still countable. Then the continuum walks in and cannot be placed on the same list at all. Picture our endlessly expanding hotel from the running gag. Aleph null guests can occupy rooms numbered 0, 1, 2, 3. Another countable bus arrives, and the manager shifts everyone to even rooms while putting newcomers in odd rooms. Crisis solved. Now one guest arrives for every real number between 0 and 1. There is no room assignment that handles them all. This hotel can absorb infinitely many buses and still lose to one interval. The interval looks tiny on screen. Its guest list is the larger infinity. Decimals use 10 symbols, which can make the result feel tied to base 10. It isn't. We can strip the idea down to coin flips. Imagine every infinite sequence of heads and tails. Heads, tails, heads, heads, continuing forever. Try listing all such sequences in rows. Read the diagonal, then flip each selected result. Heads becomes tails, tails becomes heads. The new sequence differs from row 1 on flip 1, row 2 on flip 2, and so on. Same escape, infinite binary sequences are uncountable. They also describe points between 0 and 1 written in binary, aside from the same two spellings nuisance at a few values. More importantly, a binary sequence describes a choice of subset of the whole numbers. Put 0 in the subset when the first bit is 1, put 1 in when the second bit is 1, put 2 in when the third bit is 1. Every endless bit string becomes a particular collection of whole numbers. For example, 1011 means include 0, skip 1, include 2 and 3. So the larger infinity wasn't hiding in fancy irrational decimals. It was already present in the question, which whole numbers do you choose? There are more possible subsets of whole numbers than whole numbers themselves. That sounds impossible because each subset is made entirely from the smaller collection. But choosing membership independently for every element creates a space too large to list. And now the diagonal trick is about to reveal its most general form. Here's Cantor's upgraded version, and it works on any set whatsoever. Start with a set S. Consider its power set, written P of S, meaning the collection of every subset of S. For 3 objects, the power set has 8 members. Choose each object in or out. For n finite objects, there are 2 to the n subsets. Cantor proved the power set is always larger than the original set, even when S is infinite. Suppose somebody claims to pair every element x in S with a subset A sub x. We build one special subset D. Put x into D exactly when x is absent from the subset paired with x. This definition made me reread it 3 times, so watch one dot. If dot x belongs to its assigned subset, D rejects it. If its assigned subset rejects x, D accepts it. D disagrees with every assigned subset about at least one element, namely that subset's own paired x. Could D equal the subset assigned to some element k? Check whether k belongs to D. If yes, the rule says k is absent from A sub k. If no, the rule says k is present there. Either answer flips itself. So D was never assigned. This is the decimal diagonal with the costume removed. Digits became membership choices. Rows became proposed subsets. The diagonal became the question of whether each element belongs to its own assigned subset. That general proof has a slightly alarming consequence. There is no largest infinity. Take the whole numbers. Their power set is larger. Take that power set and form its power set. Larger again. Repeat. Every supposed final infinity immediately generates a bigger one by considering all its subsets. Infinity isn't a single distant wall. It has an endless upward structure with no top floor. Our hotel manager has quit at this point, which is fair. Cantor called these sizes cardinal numbers. A left null is the first infinite cardinal under the standard ordering. After it come larger cardinals, often written a left 1, a left 2, and onward, though the power set jumps don't automatically tell us which aleph lands where. That detail matters. We know the continuum, the size of the real numbers, equals the size of the power set of the whole numbers. Binary expansions give the connection. Therefore, the continuum is bigger than aleph null. But how much bigger? Is it the very next infinite size, aleph 1? Or could another size sit between them? The diagonal proof does not answer that. It builds the jump and proves the landing point is higher, while refusing to say whether we skipped a floor. And this is where a clean visual proof wanders into one of the strangest episodes in mathematical logic. The claim that no infinite size lies strictly between the whole numbers and the reals is called the Continuum Hypothesis. In symbols, the continuum equals a left 1. Cantor spent years trying to prove it. He couldn't. Later, it became the first problem on Hilbert's famous list for 20th century mathematics, which is one way to make everyone else inherit your headache. Then the story got genuinely weird. Gödel showed that the usual axioms of set theory cannot disprove the continuum hypothesis, assuming those axioms are consistent. Decades later, Cohen showed they cannot prove it either. So within the standard foundation most mathematicians use, the hypothesis is independent. You can build mathematical universes where it is true and others where it is false without breaking the usual rules. I need to be careful here. This doesn't mean every statement is opinion, or that mathematicians gave up and put it to a vote. It means the chosen axioms do not settle this particular question. Add suitable further axioms, and an answer may follow, but then people can reasonably ask why those axioms deserve the job. Our simple diagonal number has led us from changing digits to the limits of formal systems. Still, the original result stays firm in all those standard universes. The reals are larger than the whole numbers. The unresolved part is the size of the gap. Now for a consequence that I find even more unsettling. Every number we can specify with a finite piece of text belongs to a countable collection. There are only finitely many keyboard symbols, and finite strings can be arranged by length, then alphabetically. Programs are finite strings too, so there are only countably many computer programs. Each program that successfully prints digits forever can describe at most one real number. That means the computable real numbers are countable. Pi is there. Square root of 2 is there. Every rational is there. Tons of bizarre algorithmic numbers are there. Yet the full set of reals is uncountable. So almost every real number cannot be produced by any program at all. Most numbers have no finite recipe for their digits. We can prove this enormous population exists without being able to point to its typical members in the ordinary way. Be careful with the phrase almost every. Here it means the computable numbers form a set of measure zero inside the real line, while the uncomputable ones carry all the remaining measure. The familiar named numbers are an impossibly thin dust. Our minds, books, and computers live mostly in that dust because finite descriptions are the only handles we have. The number line on the screen looks smooth and available. In reality, nearly every point on it refuses every algorithmic name we could ever write. The same escape pattern turns up far beyond counting numbers. Assume every object of some kind has been listed. Build a new object that disagrees with item n at position n. The new object cannot be anywhere on the list. Computer science uses diagonal arguments to prove that some problems cannot be solved by any program. Logic uses relatives of the idea. When statements refer to their own provability, the details change and some versions get sharp enough to draw blood, but the rhythm stays recognizable. List, diagonal, flip, escape. That's why this proof matters beyond the fact that one infinity is bigger. It gives a construction for outrunning any proposed catalog. There is a lovely reversal in that. A list seems powerful because it organizes infinitely many things. The diagonal treats that organization as exposed wiring. Every row tells the escape number exactly where to differ. More orderly lists don't help. They make the target easier to see. Keep your eye on the pink diagonal one last time. Each highlighted cell looks tiny. Together, they coordinate infinitely many disagreements, one per row, with a rule short enough to fit on a sticky note. We started with decimals refusing hotel rooms. We ended with a general method for proving that certain collections, descriptions, and computations can never be complete. And there is still a loose thread here. If most real numbers cannot be described, in what sense are we entitled to say they are there?